Till last chapter, kinematics, we never cared about the nature of forces. What is the cause of motion? All that we never cared. Only thing we cared is measurement of velocity, measurement of acceleration, whether it is uniform or non-uniform. Anika, have you received the PDF that I have posted to Vice Principal?
Yes, sir. On Newton laws of motion. Yes, sir.
Yes, with the gaps and all that I have posted, right? So we'll deal with the cause of motion in this chapter. Cause of motion. Remember, before I start Newton's law of motion, I need to inform you that every body will have a property called inertia. Inertia. Remember, it is owned by everybody. How I identify this body? It is this property it is this property by virtue of which every body continues either to be in the state of motion or rest. Two things. It is this property by virtue of which every body continues either to be in the state of motion or rest. Everybody will possess that. So what changes this state? Force changes this state. Remember, mass of the body is a measure for inertia. I mean, more is the mass, more high is the property inertia. So now how to understand Newton's first law of motion? First law of motion. Right. Honestly, the exact terminology that I should use is if the vector sum, if the vector sum of all forces acting on a particle, if the vector sum of all the forces acting on a particle is zero, okay? I repeat, if the vector sum of all forces acting on a particle is zero, then and only then the particle remains unaccelerated. If it means if force is zero, acceleration is zero. That is the observation. Or vice versa. You can write it anyway. You can write it anyway. See, remember when I am speaking about this particular terminology, when I am applying this law, I am in an inertial frame. To apply this law, one must be in an inertial frame. Then the question is, what is inertial frame? Inertial frame at rest with respect to ground, or frame moving with constant velocity. మళ్ళీ ఇది ఎవరి పరంగా with respect to ground. With respect to ground. So this is inertial frame. Why I will explain. In a accelerated system, I'll try to explain like this. So imagine a system like this. This is having wheels and it's on a floor. Remember, you have applied a force F on this. As a result, it has an acceleration. Good. Now, imagine a block placed, let us say this is A, this is B. Imagine that you are in a stage where the observer is in the frame A. Remember, this observer is moving with acceleration A along positive X direction. In this, any doubt? Vishwak, do you have any doubt till this point? Vishwak attended. Right. Anika, any doubt till this point?
No, sir.
Right. Now, what if I observe B with respect to A? With respect to observer A, right? When observes B, what happens? He finds that B will experience an acceleration A backwards. This is what we have seen in relative motion. Whereas with respect to observer A, when observe B, he will find that B is experiencing an acceleration A. In reality, there is no force acting on B. There is no force acting on B. Only force is acting on A. So what have you seen in this case? There is no force, but acceleration is not equal to 0 against Newton's first law. Please tell me what went wrong. I just introduced the first law, and now I am telling first law is wrong. What went wrong? Can someone please help me? Soumya,
Sir, it's not in a
Varun,
frame.
Chapra.
Sir, Observer A is not in an inertial frame.
Correct. So if you wish to apply Newton's law, if you wish to apply Newton's law, what is required? You should be an inertial frame. Got the point? Any doubt till this point? Any student in this class? If you have doubt, you please ask me. If you have any doubt, please ask me. So therefore, it applies only for inertial frame. Okay? So therefore, there are some frames of references in which Newton's first law is measured. Okay? And such a frame is called inertial frame. I'll rewrite, restructure my statement now. A frame of reference in which, okay, Newton's first law is valid okay, is called an inertial frame. Inertial frame of reference. I should say inertial frame of reference. A frame in which Newton's first law is not valid is called an non-inertial frame of reference. All these are basics which we are about to discuss now, and these basics we will use for the next 8 to 10 months. Okay? So therefore, this is very important observation. One more important point. All the frames moving, okay, uniformly with respect to an inertial frame, okay, is also an inertial frame. But uniform. Right. I'll try to explain the same. For example, you consider the same arrangement. This is a container moving with constant velocity. Let this be A. And there is a stationary observer at O. Let him be B. He is a stationary observer. And he is an observer moving with constant velocity. And in fact, they are observing a situation where an object is moving with an acceleration a. At an instant, the coordinates are like this: xa, xc. I'm asking you, do you have any doubt till this point? Any student? Do you have any doubt till this point? Boys and girls, any doubt in this point? Have you understood my representations? First of all, there are two observers. One is B, the other is A. B is stationary observer. A is an observer moving with constant velocity, and C is an observer who is moving with constant acceleration. So now I am defining, well, at any instant, velocity of C with respect to B is defined as dxc by dt. dxc by dt. Next, dxc by dt. And one more important point, acceleration of C with respect to B is defined as d square xc by dt square. Next, Anika, on Saturday, I have instructed to arrange backup class on calculus. Is it happened? Anyone just please confirm?
Yes, sir, it happened. It was taken by Prakash.
Right.
He explained differentiation.
Right, right. Similarly, where the position of C with respect to A is nothing but xc minus xa. Right. Now with this, velocity of C with respect to A is nothing but dt by dt of xc minus xa. This is nothing but velocity of C with respect to A. This is nothing but that instant velocity of C minus velocity of A. This we already know because we have done this in the last week. Acceleration of C with respect to A is VCA by dt, which is nothing but AC minus 0 because you are moving with constant velocity. What have you noticed? In this, I have noticed that acceleration of C with respect to B is the same as acceleration of C with respect to A. Both these two observers measured same acceleration. Both of these two observers measured the same acceleration, which means why it is the same? Because both are inertial frames. Suppose if this is moving with an acceleration, then this is wrong because this term, I'll explain the same. Suppose if the acceleration of A is not equal to 0, then what happens? Acceleration of C with respect to A is acceleration of C minus acceleration of A. Whereas acceleration of C with respect to B is acceleration of C. Remember, in this case, acceleration of C with respect to A is not equal to acceleration of C with respect to B because A is no longer inertial frame. A becomes non-inertial frame. That's the reason. Okay. Okay. Now, this is what my observations are related to first law. Any doubt, please ask me. So, what is the highlights of first law? Highlights of first law. First, it has identified that a property inertia for every body. Two, it has introduced a concept called force. Prior to first law, no one knows force. Force is responsible for change of state. And last but not the least, if acceleration is zero, force is zero. This is how we have defined equilibrium. These are the highlights of first law. Right. Now we will move on to the second law. See, before I move on to the second law, please try to understand. There is a term called momentum. There is a term called momentum. Actually, I should say linear momentum. Linear momentum. P bar is equal to mv bar. This is the definition. Linear momentum is P bar. Till we have measured everything in terms of velocity, but a train engine moving with 1 meter per second and a shuttlecock moving with 1 meter per second are not the same. The total quantity of motion associated with the body is linear momentum. Remember, it is a vector quantity whose direction is along the direction of velocity. Now, in an inertial frame, again, what is Newton's second law? You know, when there is acceleration, that disturbs the velocity, that will change the velocity. So the Newton's second law statement is, in other words, defined as the net force acting on the system is nothing but time rate of change of momentum. This is Newton's second law. Again, this is in inertial frame. This is how you will apply in inertial frame. So therefore, inertial frame of a system, in an inertial frame of a system, net force is time rate of change of momentum. Suppose if mass is constant, fixed, it is not losing or gaining the mass. Sir, what is the meaning of losing or gaining the mass? Suppose if it is a sandbag and sand is leaking out, and you are taking sandbag as a system, then you are wrong in that case. So sandbag, you cannot apply in this form. Similarly, there is a container where water is pouring in, and you are taking the container with the water at a given instant also, you cannot apply in this format. If mass is constant, then net force is mass times acceleration of the system. Suppose if mass is not, another way of writing the same thing, dP bar is F net times dt bar. Now you take the total integration on both the sides. This is nothing but P final bar minus P initial bar is integral F net times dt. You know, this is called impulse. This entire term is called impulse, and this is called change in momentum. Change in momentum. So therefore, impulse is numerically equal to change in momentum. This is also a part of Newton's second law. For example, if you are plotting a graph, taking force along y-axis, time along x-axis, you may find a graph like this. I am just giving an example, guys. Now, in this, the entire area here, this entire area is defined as F dt. This is nothing but change in moment. This area is called impulse. That area is called impulse. Okay. So this is the introduction to Newton's second law. Now we might apply different cases in the process of applying Newton's second law. Newton's third law, I'll just introduce bit later. Right. So now I have introduced two laws. One is Newton's first law, the other is Newton's second law. And remember, we are now focusing on different types of forces. The first type of force, when I am writing about types of forces in nature, basically there are four forces. Whatever you see in nature, one is gravitational force. Next, electromagnetic force. Next, nuclear force. Next, weak forces. Remember, in this, you can have the nature of these forces can be anything between masses between, for example, force between sun and earth, force between satellite and a planet. All these things comes under gravitational force. Generally, it is mass based. Okay, it follows universal law of this law, universal law of gravitation. So Like, we will anyway define this later strength, but I think is already known part for you. On the basis of these pairs, we will operate. Electromagnetic forces. So electromagnetic forces are, it's like Coulombian force. Basically, this is a Coulombian force. Charge based 1 by 4 pi epsilon naught q1 q2 by r square. Basically, so charge based. Uh, I mean, charge at rest or charge in motion or whatever it is. Anything related to that. Next, the other force, nuclear force. Between the nucleons, neutron, proton, proton. Whatever the force that comes under nuclear force. Okay. Basically, this works only inside the nucleus. And this is the situation where the distance is less than some 10 power minus 14 meter Fermi, in a range of Fermi. Okay. So therefore, nuclear forces are very strong actually out of all the three forces. They are very short range forces. Both are long range forces. It is a very short range force. Right. Next, weak forces. We'll call this as weak forces. Very subatomic particle. Like, for example, force between neutron and neutrino, something like that. Very small. You cannot you cannot feel it as if that the subatomic, even lesser than proton, neutron size particles, whatever it is, that force is weak forces. Remember, all these we will discuss a later stage. Even gravitation, we will discuss it at a later stage. If someone is asking me doubt, feel free to question me. Just introducing forces. Remember, I am not going to use any of these forces for the next 2-3 months. I've just introduced the forces. Right. Till this point, any doubt? Any student? Any student? Till this point. Right. Fine. But we are not going to use any of these forces. We are not going to use any of these particles. We are going to use a different type of forces within what we have learned. For example, out of all, strongest is nuclear, undoubtedly. Right. See, the nature of the forces which we are using, nature of forces which we will use in mechanics basically are like this. First force is weight normal reaction force. I will explain every force in detail. Weight force, tension force, It can be in a string or rod. Spring force, friction. For liquids, viscous force. See, you are using any force, these forces, pressure force. You are using forces, you are using any of these forces only in mechanics. Maximum, these are the only forces which we are about to discuss in mechanics. Let me start one by one. Right. Now, first, we will discuss about the weight and normal reaction force. Suppose if someone is missing this class, no, so they don't know anything about force, they don't know anything about normal reaction. The problem is they cannot do any problem. But their main logic is to enjoy holidays. What will you do when he is back after enjoying holidays? Entire 1.5 years he will suffer. Weight force and normal reaction force. Okay. Now imagine this is some floor like this. And you have a block like this. Right. Now, this block will experience a downward pull by the Earth's gravitational force, which we will call as weight, mg. But the question is, the block is still at rest on the floor. How is this possible? Tell me. How is this possible? There should be some other force that should counter this situation, yes or no? How is this possible? Anyone in the class? There should be some other force to counter this. Remember, this is the block and this is the floor. How is this possible? This is possible only when the floor also exerts an equal force. Otherwise, net force 0. If it is not happening, there should be acceleration. Practically, nothing is accelerated there. The block stays there only. It is not going down. It is not going leftward. It's not going rightward. It's there only. So therefore, it should have 0 acceleration. So how is it possible? How is it possible? Normal reaction force should act on the block to counter this. So therefore, the floor is exerting a force called normal reaction to make the net force 0 in the y direction, which means, see, upward force you will take as positive, downward force you will take it as a negative, so 0. So therefore, in this case, N is equal to mg. This N is called normal reaction force. This is called weight force. Right. Suppose if the situation is different, in fact, you have the situation like this. The block is like this, and it's an inclined plane. Then what happens? In this case, whatever the position is, weight always acts vertically downwards. Now, this force you can resolve into two components. One is along the inclined plane. The other is normal to the inclined. The other is normal to the inclined plane. యాక్చువల్గా పెండింగ్ ఏమో కింద వేరే రెగ్యులర్గా మనం చూపించుకునేది ఫస్ట్ రైట్ 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 రైట్. Now, if this is a theta, this is a theta. Because geometry, 90 minus theta, theta. And this will become mg cos theta. This will become mg sin theta. Now here, this is your vertical now. This is your vertical. This is where you see the vertical now. So therefore, now the normal reaction force is like this. In this case, now you take this as y-axis. You take this as x-axis now. So we are worried about y only. Sigma f net in the y is 0 because it is still in contact with the floor. No acceleration in y direction. So therefore, in this case, normal reaction is mg cos theta. I hope I have successfully introduced two forces, weight force and normal reaction force. When will I fail in doing problems in physics? If I compromise now. If you are compromising now, you will fail in later stage. Now tell me, if you still have any doubt, ask me now. I am teaching from zero. Are Varun, respond.
Yes, sir.
ఇంతకన్నా బేసిక్ ఏమన్నా కింద ఉంటుందా మీకు చెప్పాల్సింది? మీరు ఆలోచి చెప్పండి ఒకసారి, బికాస్ సిఓ స్కూల్ కాదు ఇది.
లేదు సార్.
నేను జీరో నుంచే చెప్తున్నానా?
ఎస్ సార్.
రైట్. Tell me you have any doubt on this. If you have any doubt on this, I am prepared to discuss on this further. Otherwise, I'll proceed. Akshat, may I proceed further?
Yes, sir.
Right. Now I will use a tension force. Tension force usually two types, elongative in case of string, elongative or compressive in case of rod, light rod. So first we will deal with tension force in a string. Right. Now imagine a situation like this. This is some roof. And you suspended a block like this. In this case, whatever it happens, this block will experience a downward pull due to the attraction of the earth. To make this at rest, equilibrium, you require one more force. What is that force? String will exert a force on the block. Now remember, you are drawing the force exerted by the string on the block. This is force of string on the block. Right. This is acting on the block. Now you draw the free body diagram of the string. This is end A and this is end B. End A, remember the wall pulls the string up with T force at end A by the wall or roof. I'll later use the word roof. By the roof on string at end A. Similarly, the block will also pull the string B downwards by a force. Now tell me what is the effect of these two tensions? Anyone? What is the effect of these two tensions? The intention of these two tensions is elongative or stretching string. So this is how tension force acts in the string. At any point you take, it is the same tension throughout. We are usually taking, unless or until mentioned, usually we will take massless string. If you are taking massless string, tension is the same at every point of the string. Now I am asking you again, have you really understood this concept? Fundamentally, I taught you this. Anika, have you understood this?
Yes, sir.
Paka,
Yes, sir.
right. But in a rod, tension force exists in two ways. I'll explain that. For example, in a string, it is always elongated. Now we will work on the tension force in a rod. For example, you have a rod like this. Held vertically, and that is the floor. And now I have placed a block on this. See, if I see the block will experience weight force down. But still the block is at equilibrium. How is this possible? Tell me. The block which is on the top of the rod is at rest. It very clear. There is nothing, no confusion part in this. But how is it possible that this block remains at rest? Tell me. No one in the class? No one. Hanvit, can't answer this?
Sir, the normal reaction from the rod will.
Yes. Rod is exerting a force. You can call it a normal reaction that keeps the block at rest. Fine, understood. Good. Now, therefore, study the rod. We assume a light rod which is not having any weight. Now, what is happening to the rod? The block is exerting a force N on the rod. I'll just try to explain much more claritatively by drawing this separately. Pritam, no Cheiko. Right. సపరేట్లీ మీరు పాఠం వినకుండా ఈ పనులు చేస్తూ ఉంటే మీకు ఏం చెప్పాలనిపిస్తుంది? రైట్, దిస్ ఇస్ ద రాడ్. నౌ యూ have clearly understood the rod is also in equilibrium. So therefore the floor should also exert. The floor should also exert This is the situation. This is the situation. Now, what is this? Force of block on rod. What is this? Force of floor on rod. Right. Can you please tell me? Of course, here also sigma F is 0. But what is the nature of these forces? What are these forces trying to do the rod, Anika? Up and down. The nature of forces, what is that they are doing on the rod? Tell me. Anyone in the class?
Sir, compressing.
Yes, they are compressing the rod. So in this case, tension developed in the rod is compressive. You should take that tension as negative, actually. Okay, so tension in a rod is compressive in this case. It is a compressive. For example, another case I will try to show you. You have a rod like this, light rod, fixed to the wall, and you are applying a force F here. In this case, the nature of the forces on the rod are elongated. So in this case, elongated tension develops in the rod. So in a thin rod, compressive and elongated tensions are possible. Whereas in a string, always tension is elongated, not compressive. Always the tension should be such a way that to stretch the string. Right. Any doubt till this point? Please ask me, because I am going to go for the spring force. Friction, pressure force, we will deal it later in the next coming chapters. But right now, if you have any doubt, please ask me. May I go further? Dhananjaya, may I go further?
Yes, sir.
Right. Are Raghava Reddy, Uchava?
Yes,
No.
sir.
Uchava Raghava? Very good. Right. Next.
Yes, sir.
Next concept is spring force. See, basically, the structuring of the spring will be like this. It's like a helical state, right? We call usually L naught as the natural length or relaxed length. We will call this as a natural length or relaxed length of the spring. Now, when you apply in this situation, you have applied a force F like this. As a result, the spring displaced by some x distance. Now you will call as elongated. Spring is elongated and the spring will now experience two forces. Kx, Kx. This is the free body diagram of the spring. Whereas the force exerted by the spring on the wall will be like this. Kx, let this be point A. At A, you are applying F. The spring will exert Kx force. And this comes under elongative type force. Okay. This will come under elongative type force. Whatever that you are seeing now, elongative type. Right. There is another case possible. There is another case possible. You know what is that? This is the natural length actually. And you have applied a force F like this. And this case is called a compressed state. In this case, the free body diagram of the spring will be like this. Kx, Kx. The free body diagram is like this. On the spring, force is like this. Whereas, okay, the spring will exert force on the wall Kx, force on the point at A, Kx, besides you are applying a force F there. So this is how the spring will exert force. Remember, relaxed length. Remember what happens when it is stretched. Remember what happens when it is compressed. Remember, for spring, you need to remember one thing. You will call this as a force constant of the spring. Force constant of the spring. Remember, if it has a natural length, the general property of any spring satisfies this condition. K into L naught is a constant. Force constant or spring constant for every spring, that should satisfy this condition. KL naught is constant. Now, for example, you have a spring like this. natural length L0. Now you cut this into two parts. L1, L2. Then spring constants will change as K1 and K2. And in fact, you cut the spring into two parts such that L1 plus L2 is L0. Then K1 L1 is same as K2 L2 is same as K into L0. That's the deal. So if you cut the spring into two parts, they will satisfy this condition. I'm just giving basics. On springs, I will discuss a separate class again. I just introduced basics. I first introduced weight and normal reaction force. Thereafter, I have used tension force. Thereafter, I have used tension force in a rod, elongative, compressive, spring force. Entire next 4 months, you will play on these things. I am asking you again, if you have any doubt, please ask me. Else, I will go for the next stage of my discussion. Boys, any doubt on this? Just asking you again. Feel free to discuss about this. Any student? Right, no issues. Now we will learn how to draw free body diagram. How to draw free body diagram. I can see a message. No doubts. Thank you, Isaac. Right. I will send these notes in the group, undoubtedly. Don't require to note this. I'll just send you this. Right. See, there are certain rules and regulations while you are doing mechanics. First, you need to know how to draw free body diagram. If you don't know how to draw free body diagram, then you cannot solve any question. Therefore, the first rule before you start is free body diagram. First rule is identify the body whose free body diagram is to be drawn in the system. That is the first thing that you need to do. Second thing, identify forces acting on this body, on the body which you have identified. Identify forces acting on the body by surroundings. And represent them with vectors. That is the second point. The third point, represent and ఇందులోనే రాసేస్తాను and represent it as a block or point. Do not represent force acting by this body on surroundings. This is a very important caution. Don't represent the force exerted by this body on surroundings in the free body diagram. 4. Resolve net force along X as well as along Y. Resolve all the forces, net of all the forces, totally along X, totally along Y. Then what happens is, you simply apply sigma fx is max, sigma fy is may, sigma fz is maz. I'll just show you simple example of this. For example, you take this as an inclined plane. Here is your block. Now I am assuming different forces acting on this. One is a force F1, which is parallel to the floor. Another one which is acting F1, right, F2, which is normal to the inclined plane. The third one is weight. The fourth one is normal reaction. Remember, I have drawn the free body diagram. This is how I have drawn the free body diagram. See, in this case, with its immediate, represent it as a block or point with its immediate surroundings. So I have shown with surroundings. But the inclined plane with horizontal represent as it is, I have represented. Now what I will do? I will define this as x-axis. I will define this as y-axis. That's all. Now I will try to represent the forces. Now this block, either I will represent it as a point or a block, no issues. Now I will represent the forces. Now you see on y direction, what are the forces? One is F2. The other is normal reaction. And the other one in the same direction is the weight component mg cos theta. There is also another one which is F1 sin theta. All these are the forces in the y direction. So what are the forces in the x direction? One is the weight component mg sin theta. The other is F1 cos theta. Right. Now, have you identified what I have done in this question? Everyone in the class, please. Be honest. So in this, see, I have represented all the components of y, all the components of x. Fortunately, it is in contact. If it is in contact, acceleration is 0. So therefore, sigma fy 0, because it is in contact. So all the downward forces, F2 plus F1 sin theta plus mg cos theta, all are downwards. Only one force upwards, N. Right. Similarly, sigma Fx is equal to MAX. Downwards, I'll take negative because positive x is represented like this. So therefore, mg sin theta minus F1 cos theta is MAX. Remember, I have applied Newton's second law. I got Ax, which implies Ay is equal to 0. So it has only one acceleration, that is Ax. See, what I have done, I am explaining you again. Here, what is the system? Fortunately, block and inclined plane is the system. What is that I am identifying? I am identifying that the block is my selected body for which I am about to draw the free body diagram of the system. What I have done, I have represented the block with its immediate surroundings, like as it is shown as inclined plane. Second point, I have identified that F2, F1, N, mg, these are the forces acting on the body. Of course, the block also exert force on the inclined plane, which I did shown in this free body diagram. Right. Now what I have done, I have represented the block as a point, and what I have done is I have resolved all the forces into y components, x components separately. For separately, sigma fx 0, sigma fi 0, likewise I have done. So I got the situation. In this situation, I got ax, ay 0. Students, do you have any doubt on this? Ask me now. Because with this, the fundamental part discussion is done. So please ask me if you have any doubt. Every student in the class, you have right to question me till now. The moment when I start applying things, you will have no scope to, I mean, even that time also you can ask. But the issue is, I'm giving a fair chance right now. Dhananjaya, have you followed everything?
Yes, sir.
Sri Shanti, have you followed?
Yes, sir.
Right. Next. I'll start working on the things. Right. Now you see, let us take this as the first system. In the figure shown, the mass of the ball is M and the string S3 is horizontal. Find the tension in the string S1, S3, and the strings do not have mass. Fine. In this case, this is mg. And you have some tension T1 here. You have some tension T1 here. You have some tension T2 here. You have some tension T3 here. Right. Now you take this point. This point is experiencing forces like this. T2, T3, T1, which is equal to mg. And the system is in equilibrium. So from vectors, you can write Lami's theorem here. So T1 by sine total is 180, 180 minus 45. T2 by, చూడండి మన వెక్టార్స్ చెప్పాను నేను బేసిక్స్. Someone if who is not following this, he fails in understanding what I'm writing, right? Every class is important here. T2 by this is 90 plus 45. Next, T2 by T3, earlier one thing, T1, T3 by, next, T2 by sin 90. This is Lami's theorem. Done. Now this is T1 by 1 by root 2 because sin 180 minus theta, sin theta, sin 45, 1 by root 2. T2 by cos 45, which is also 1 by root 2. T2 by 1. We know T1. T1 is mg. So therefore, literally T2 is also mg. Yes. Why? Because we have these two terms cancel. T2 becomes T1. Right. What about now T1 is equal to T2 is equal to mg. What about T3? T3, right. T2 is root 2 times T3, which is root 2 mg. So I have given with the magnitudes. Now I am asking you, do you have any doubt in this question? Don't ask me how you got Lami's theorem, which I have done long back. Very simple. The proof is the application part is like this. If we have three forces, which is keeping the system in equilibrium, P, Q, R. Now this is theta 1, this is theta 2, and this is theta 3. Then what I have given Lami's theorem, P by sin theta 1 is equal to Q by sin theta 2 is equal to R by sin theta 3. This is Lami's theorem. I have applied simply that. I am asking you now, any doubt, any student having doubt on this part? Akshat, do you have any doubt?
No, sir.
Hemant Kumar, do you have any doubt? Right. Sai Priya, do you have any doubt?
No, sir.
Right. Fine. I am going on to the next. We'll do one after the other. Yeah. Everyone try this. What is there on the board? Try this. We have only 15 minutes time. My major approach of today's class is to introduce. So tomorrow's class is going to be a very beautiful class. I am going to discuss hardcore important applications. Tomorrow, day after tomorrow. Thursday, again, I will give you some backup class for mathematics. Now, Friday, Saturday, I will discuss strictly Olympiad questions. See, while I am preparing these questions, I am collecting 4 to 5 books, remember. Which means you don't require to purchase a single thing from any of these things. Someone was asking when are offline classes? Friday, Saturday onwards, you will have Friday onwards, you will have online class, offline classes. We committed only for 1 week. I have given that till Thursday. Right. The breaking strength of the string connecting the wall and the block is maximum tension. In this case, is 175 Newton. Find the magnitude of weight of the block A for which the system will be in stationary. I don't see any different question here. I'll write this as tension T. I will write this as tension P. And I will write this as tension A, which is equal to MAG. Right. And don't forget the angle 30 degrees over here. Now I am applying Lami's theorem. T by sine 90 is equal to, right, TA by sine 180 minus theta is equal to TB by sine 90 plus 30 degrees, which implies T is equal to TA by sine 30 is equal to TB by cos 30. What I know is TB because this is TB and this is TB. Lot of students will do mistakes in applying free body diagram itself. So you may ask me, how do you know this is TB? Are B is in equilibrium. You said 175 newtons, the left side acting. String will pull B by TB. And the same string is at the other end. And that the other end will pull point O with TB. That's what I have written. Exactly that's what I have written. Because all this is a single string. So therefore, by the way, I know TB. So TA is TB cot 30. As you mentioned, TB as 175 cot 30 is root 3. By the way, what you want? The mass of the block B. Find the magnitude of the weight of block A. Fine, no issues. TA is MAG, which is equal to 175 into root 3. So MA is 175 root 3 by 10 kg. I have nothing to do with the mass of B. Why? Because weight of B is actually balanced by the normal reaction force on the ground. That is balancing. So therefore, I have nothing to do there. Now tell me, have you understood this question? Are you still having any doubt? Participants. Sai Priya, do you have any doubt?
No, sir.
Shruti. Right. Okay. Are this? Okay, fine. Why don't we try this? I want this question to be done. Now you need to draw the free body diagram of this situation, right? So what are the free body diagrams? See, one thing is very clear at this point. At this point, I'll call this as normal reaction 1, and that passes through the center of the sphere. All are smooth surfaces only. And here you have another point. Normal reaction N2, which will pass through now at this point. What is happening? Like to please understand. I'll take this point as my free body diagram. That is the point upon which I'm observing all. One thing I can see is that N1 is passing through like this. Another thing that I can see is N2 passing through like this. The third thing that I can see is weight force. Remember, which I can show that clearly in the diagram like this. Remember, this is 90 degrees. This is 90 degrees. This is 60 degrees. Can you please tell me what is going to be the total angle here? Anyone in the class? In the rectangle.
120.
Yes, exactly. Correct. 120 degrees. If this is 60 degrees, this is 120 degrees. N1, N2, Mg. Now this angle is 120 degrees. Clear. Right. I have drawn the free body diagram. This is the free body diagram. Your normal reactions. Remember, undoubtedly here N1 is same as N2 because symmetrically distributed. If the angles are not symmetrically distributed, like for example, left side here, if it is some 30 degrees and here it is some 60 degrees, then the normal reactions are different. In fact, it is bisecting actually. You can see it is bisecting. This is also 60 degrees and this is also 60 degrees. So therefore, because of this reason, I can say normal reactions are same. So which clearly indicates this is 120 and this is also 120 because they are same. Trust me. Now in this case, Lami's theorem states N1 by sin 120, N2 by sin 120, Mg by sin 120. So clearly N1 is equal to N2 is equal to Mg. That's all. Any doubts? Please ask me. Any student in the class. What I notice is after 1 hour, last 10 minutes, people stop dropping out from the classes. The problem is the same parent will come to me some other day and asking for sir, marks. You don't have the discipline of listening to the class and tell me how is it possible. I'm teaching only 20-25% of what I would have usually taught in a regular class. And your work also very slow. You are not doing any work because of XYZ reasons. Right. Any doubt on this question? Please ask me. Boys. Kundana, do you have any doubt in this? Kundana.
No, sir.
Right. Now try to do this question. A heavy rope, mass M. Go through this. Remember, whatever it is in equilibrium. So I am assuming that T2. This is a theta. It is mentioned that it is clearly the rope makes an angle theta with the ceiling and an angle of 90 with the vertical, which means clearly it is horizontal. T. Yeah, this is clearly mentioned in the question. Now, please, I am drawing the free body diagram of this rope. Somewhere here you will have weight part. Now I am taking the entire thing as a point. What are the upward forces right now? One is T2 sine theta. The other is mg. What are the horizontal forces? One is T1. The other is T2 cos theta. This is the free body diagram. And the system is in equilibrium. Sigma fx 0, sigma fi 0. Who said this? It's in equilibrium. It's not, you can see it's static. So from this you can conclude T2 sine theta is nothing but mg. And T2 cos theta is nothing but T1. So equation 1, equation 2, equation 1 by equation 2 implies tan theta is mg by T1. Or T1 is mg cot theta. That's it. T1 is done. You want T1 only, find the tension forces at the two ends of the rope. Okay, the other thing that I can give is T2 cos theta is T1 is what you have uttered here. So T2 is T1 by cos theta, which is nothing but mg cot theta by cos theta. So therefore T2 is mg by sin theta. So I have given the tension at both the end. Don't ask me, you answer in terms of theta. You have given in the question about the information related to theta. So I have answered. Please try to understand at every point, the horizontal part tension balances. Vertical part, you see, it should balance the weight. Right. Any doubt in this question, please ask me right now. If you have any doubt, please ask me right now. Are we clear? Right. Next. So that's all for today. So I'll post the notes after the class.